Hello, everybody. My name is Mr. Bond. Everybody say, what's up, Mr. Bond? Great. Today we're going to be talking about energy. Humans have a lot of energy. In fact, everything has a lot of energy. It's actually quite easy to talk about energy because energy is everything. And humans have learned to harness this to make our lives easier. For instance, I have a rocket launcher right here, and it's full of many different types of energy. For one, it's got atoms in it, and anything with atoms or mass has energy. If you're able to split those atoms apart, then you get massive explosions that are way bigger than you want and almost too much energy. And it takes a lot of energy to split those atoms apart. Also, it has thermal energy. I know this because I can touch it. If I hold on to this, my hands don't freeze off. Anything above absolute zero has thermal energy. It's got heat, which means that all these molecules actually are moving around just a little bit, enough to hold their energy. Beyond that, if I wanted to light this on fire, who wants me to light this on fire? No, we're not going to light this on fire. If I lit it on fire, it would express a chemical energy. The chemical energies oftentimes will put pollutants into the air. We don't like to burn plastic, so that's not a very good idea. Also, it has potential energy. If I lift this up, does it have potential or kinetic energy if I'm holding it right here? If you said it's got potential energy, you're right. It has the potential to do work. What do you think will happen if I let it go and all of the air is forced out of this little straw? What do you think is going to happen to my little rocket? Let's find out. So I have potential energy. When I let it go, it's going to be kinetic energy, energy moving. Let's see what happens. 3, 2, 1. Ooh, perfect. Yes. So I turned potential energy. I used my own work and I picked it up and I let it go. I turned it into kinetic energy and I was able to make a launch. So we're going to be talking all about how to turn our energy into something that works for us. Now, right here is one of my very favorite inventions. This is called a Stirling engine. And what's great is all I had to do is put a little hot water in there. And once I started turning, it actually keeps turning. Now, think about this for a minute. If I have hot water inside of my mug, there's a metal plate on the bottom, and then I have my secondary piston down here and a primary piston up here. How is it making it move? Well, what happens, if you've been thinking about this and wondering what's happening, is it's heating up air molecules. When you heat up air molecules, they start to move around and push around. As it pushes it around, it's pushing the piston up, which allows this other piston to move. And eventually we get some mechanical motion. Now, what's cool about this is we've turned hot thermal energy into movement. And now we can travel across the country because we're actually able to get mechanical energy from our heat. So that's pretty cool. That should keep going for quite a long time. You can watch it as the show goes. As long as the water stays hot enough, it'll keep the bottom plate a lot hotter than the top plate, which allows our Stirling engine to move. Now, to go a little further into that, the molecules inside of the Stirling engine, when you heat them up, push away from each other. They want to run around like crazy. So all of these yellow parts we can think of as H2O molecules. What is H2O? Water, right? Yeah, sure. Water is inside of our ice and our rain and all that sort of thing. When we heat it up, it turns from ice, which is what it is here, and it starts to move around a little bit. It starts to flow around, and it has more energy. As we heat it up even more, all of those molecules start to bounce around the whole room. It turns into a gas, and we breathe it in. We can't even see it because the molecules are so far apart. And it goes back and forth. As it gets colder, it loses its energy. Those molecules start to chill out, and they just hang out, and they fall asleep. But we use all sorts of other things to capture our energy. I'm going to start with this. I'm thinking of a word that starts with M. It picks things up, and it's not your maid. What is it? If you guessed magnet, you're totally right. I've got a very powerful neodymium magnet right here. And they're actually so strong that if you get them too close to anything that attracts a magnet, you can actually pinch your finger pretty badly. Now, I have a question for everybody. What do magnets stick to? metal. If you said metal, you're totally right, but there are 3 different metals that it sticks to. I think a lot of people would say iron, right? And if you said steel, you're also right. But by the way, steel and iron are basically the same thing. So that still just counts as 1. The next one is our 5-cent coin. Shout it out if you know it. Nickel. Good. Yes, nickel. So we have iron and steel. Nickel. And the last one, does anybody know it? Starts with a C, ends with an obalt. Anybody? Cobalt. Iron, nickel, and cobalt are the 3 metals that stick to a magnet. But does it stick to copper? No. Does it stick to a plastic tube? No. So what happens if I drop my magnet down through my tube? How long do you think it'll take to get from the top to the bottom? Just gravity pulling it down, maybe 1 second? I think you're probably right. Let's see if you're right. Let's all count together. On your marks, get set, go. 1. Yeah, 1 second. Of course, we always need to do every experiment a couple times just to make sure that it's still working the same way. On your marks, get set, go. 1. Yeah, still 1 second. So knowing that, it takes about that long. And we've got a copper pipe that's about the same height. How long will it take to get through the copper pipe? Again, we know it doesn't attract to copper. So I would agree, probably about 1 second. Let's find out. On your marks, get set, go. 1, 2, 3, 4. Wait, that was kind of weird. 4 seconds doesn't stick to copper, right? No, it doesn't stick to copper. Let's see if it still is working. 4 seconds. On your marks, get set, go. 1, 2, 3. Okay, so I counted a little slower that time, but it's about 4 seconds every time. Something odd is happening here. What you need to know about this experiment is that magnets are basically the same thing as electricity. We might say they're 2 parts of the same coin, right? Two sides of the same coin. Magnets have a negative and a positive. We might say a north pole and a south pole, right? But so does electricity. It has a negative and a positive. And when we take and we get some movement, some mechanical motion, we actually are creating magnetism now where there was none before. And it actually is slowing it down by creating electromagnetism, by moving that negative and positive down through the copper. We are creating magnetism. Now, I know that seems kind of weird, but what would happen if I made the magnet a little bit bigger? Who says it would take longer? Who says it'll be shorter? Who says I have absolutely no idea, Mr. Long? If you have no idea, that's fine. Let's just find out. On your marks, get set, count. 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds. So it took longer. The bigger the magnet, the longer that it took to get down. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so at 8 or 9, if we were doing this experiment in a lab, of course we would use timers that counted the same amount of time every time. But what we're finding is that the larger the magnet, the longer that it takes. Now let's talk about this for a minute because this is fascinating. This is the same technology that we use to create our electricity. Yeah, absolutely. All we have to do is something very similar. This is called Lenz's law. Remember, magnets stick to iron, yes? And we also saw some interesting characteristics of copper. Well, if you're able to take these 2 things, if you wrap copper around iron, and then you spin magnets around it really fast, instead of using an electrical conductor to create a magnet, you can use those spinning magnets in motion to create electricity. And that's what happens when we burn coal. We burn coal and it heats up water. And then that water pushes the magnets around and around through steam, and it creates electricity on the other side, and we store it and we use it for later to get ourselves across the country. There's a problem with burning coal, isn't there? Let's go ahead and go to our burning experiment. I have something here that is going to start off very dangerous. This orange chemical right here is called ammonium dichromate. Everybody say ammonium dichromate. And ammonium dichromate is going to burn and create a totally different thing. Right now, it is not safe for me to touch. But if I burn it, it's going to create a new thing. One thing it's going to create is carbon dioxide gas, water vapor. It's going to put off nitrogen into the air. The same thing happens with coal. When we burn it, it puts off lots of stuff into the air. And we don't always want that because it contributes to global warming problems. Let's go to the close-up camera and watch this beautiful burn. What's going to happen when I get this lit and start burning it is it's going to start doing a beautiful reaction. Everybody watch closely. This is called exothermic. If you watch closely, you can see steam rushing off, which is how we create our energy in coal fire plants. But you're also going to see a little bit of ash. Right now, it looks like a beautiful volcano. It's really, really fun to watch as it burns. But I don't necessarily want all this stuff in the air if I'm having to burn it all the time to create my energy. So this is called a chemical energy. It's burning something to create its energy. And although it's really fun to watch, it's not very fun to breathe, and it's not a very good and efficient way to create our energy. So believe it or not, we can actually use our Lenz's law in other ways too. It doesn't have to just be coal burning to push steam to change the magnets around and around. We can also use wind power. Wind power does the same thing. Those big turbines you see out in the country, they start to turn and turn and turn, and they're actually moving the magnets in a much more direct way, which allows us to capture that electricity without ever burning anything and putting anything into the environment. The same is true for hydroelectric power. When you have a big dam, it lets water down, and that water gets moving faster and faster and faster, and it turns the magnets and it makes the electricity. So, but making a dam isn't always the best option either. So really, things like solar power, which we didn't really talk much about, and wind power might be the best options to not pollute too much. Now, all of that said, that's a great way to use renewable energy. Wind power is a renewable energy. Using the power from the sun is a renewable energy, which uses different processes, photovoltaic cells. But another thing that we want to do when we're thinking about our Earth and how we care about it is recycling. Now, who knows what this cup is made out of? If you said styrofoam, you're right on. Good, styrofoam. I have some broken styrofoam cups here that need to be thrown away. Should I just go ahead and throw this away? Well, probably not. What I would maybe want to do is recycle it. Now, if you live in certain places, you can take your styrofoam to this recycling plant and they will break it down for you and make new styrofoam cups. Who knows what the word foam means? If you think foam means it has air in it, you're right on. Absolutely. Foam means that it has air in it. And this process we're going to do now is going to be taking all of the air out of this cup. I'm going to go ahead and pour a little bit of our chemical on here. Now, this is acetone. And what it's doing is it's dissolving the cup. And I just want to be really careful not to get it on my hands because you can see what actually starts to happen to the cup. Pretty cool. I'm doing a process where I'm just taking out all the air and wait, I just got it on my hands. Actually, that's okay, everybody, because even if I got it on my hands, acetone is not like an acid or anything. It's not going to dissolve my hand. It's only going to dissolve the cup. Acetone is actually a nail polish remover if you have that at home. Now I'm putting this nail polish remover all over my styrofoam cup, but I've taken out one thing. I've taken out the foam. And if you were listening, foam means air, right? Foam means air. Now I have this very same cup, but I've just removed the air. And now I can take this very same polystyrene, that's what's left over from styrofoam after you take out all the air, and I can add more air and make new cups. Believe it or not, that's the same exact cup, just one doesn't have the air. And that's called a physical change. And we're about to do a chemical reaction in our next experiment. We're all about to make slime together, and that's going to be a chemical reaction, which is just slightly different than a physical change. And we're going to talk about that in just 1 minute. So I hope you guys enjoyed this portion of the show, and I'll see you in just a second for our next slime making activity.